Whilst the study of physics is for many a search for the truth about the universe, for us it's about being proven wrong. Physics constantly challenges our intuition, proposing unexpected ideas despite only adding one level of complexity.
Take the interaction between two planets due to gravity, the two-body problem. This is entirely solvable through mathematics we already have, but in reality, we normally see 3 or more planet-sized objects interacting at once. And unlike the two-body problem, the three-body problem has too many variables to be solved, bar a few improbable cases.
With the two-body problem, we can use their common centre of mass, the barycenter, as a fixed anchor. In the correct reference frame, the entire problem reduces to one effective body orbiting a fixed point. That symmetry is what makes the equation solvable. The motion collapses into clean conic sections, ellipses, parabolas, and hyperbolas. Now add a third mass. The barycenter still exists and momentum is still conserved, but it no longer simplifies the system. Each object pulls on two others, the force vectors constantly shift, the degrees of freedom coupled together. Adding just one more planet doesn't make this problem slightly harder, it makes it fundamentally different.
This is chaos. A chaotic system is not random, it's deterministic, but it's exquisitely sensitive to initial conditions. Change the starting position slightly, adjust the velocity by a tiny amount, and at first the motion looks nearly identical. Over time, those tiny differences grow exponentially. Two almost identical systems evolve into completely different futures, which means you don't need galaxies to see chaos, you don't even need planets. You just need gravity, or even simpler, a pendulum.
A single pendulum swings predictably and periodically, an example of harmonic motion, non-chaotic, well-behaved, but attach a second rod with a pivot, a double pendulum, and everything changes. The system now has 2 degrees of freedom, 2 coupled equations, 2 constantly interacting motions. We can visualize this using phase space, a mathematical space where each axis represents one of the system's variables. For a single pendulum, phase space is 2-dimensional, one axis for angle, one for angular velocity. Its motion traces a clean, closed loop, an orderly ellipse that repeats forever. The double pendulum lives in 4-dimensional phase space, 2 angles, 2 angular velocities, and here, instead of closed loops, trajectories sprawl unpredictably. 2 nearly identical starting points, almost indistinguishable in that 4D space, rapidly diverge into completely different paths. The geometry of chaos becomes visible.
Modelling the phase space of chaotic systems often reveals unexpected geometry. In 1961, Edward Lorenz plotted 3 atmospheric variables against one another and discovered what is now known as the infamous Lorenz attractor, a looping curve resembling butterfly wings.
This attractor does not trace a particle's movement through space, but a system evolving through each of its possible states, revealing the structure that lies within apparent disorder. Fractal geometry, where trajectories never repeat and never intersect. The equations are simple, the behaviour is not. Not every system produces strange attractors. As we adjust a control parameter, the system can change dramatically, a phenomenon called bifurcation. Small tweaks near these critical points can send trajectories along completely different paths. This is the essence of the butterfly effect. Sensitivity amplified by the geometry of nonlinear systems.
The logistic map mathematically visualises this concept. As its growth rate increases, a branching bifurcation diagram emerges, showing how tiny parameter changes produce dramatically different long-term outcomes. The butterfly effect is not mystical, it is merely the geometry of nonlinear equations unfolding.
The complexity of chaos makes studying physics so gratifying, is what sparks our desire to discover more.
Above all, it is the excitement of realising our prior understanding was incomplete.
Because this means we have more to discover.